Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series about the topic of process capability. In this lesson, I review the first 3 steps that I like to recommend as part of a method for calculating process capability. These first 3 steps cover content that was covered in prior lessons, so although I'll be reviewing the content in this lesson, it may be helpful to review those prior lessons for additional details. So for now, let's begin by reviewing again what process capability is.
Process capability refers to the voice of the process, or VOP, representing the standard set of metrics we might use to define how a process is performing or the capability of that process. Well, the example we've given before is if we have a distribution reflected here of the actual process performance. If we're following the define phase all the way through the DMAIC methodology, and the define phase here is when we're trying to understand the voice of the customer, or VOC. That's where the customer, from them, they define for us the requirements or their expectations for whatever it is they want us to perform from the process itself. Well, we might outline those based on the lower spec limit and upper spec limit, and anything within that portion refers to something that's good, something the customer is willing to pay for, the value added. And it's in the measure phase when we try to gather data, the data that we can trust, and data that we'll eventually be using to help measure the performance of the process, reflected again as process capability. So that's when we're trying to gather the data, and it's in the analyze phase that we described here where we're actually doing the calculation to figure out what is the capability of that process based off of that reliable data we collected in the measure phase. So here's where we're trying to fill out the blue portion here, where this reflects the lowest part of the range and the upper part of the range of the entire distribution representing our entire process and the performance and capability of that process. So here it's in the analyze phase then where we're defining what that process capability is, and now we have something to compare it to, that is to the voice of the customer, the VOC. And this is what's going to help us to understand the performance gap, how we're actually performing reflected here in the outer limits compared to what the customer wants or what their requirements are. Then the gaps here, these performance gaps, reflect for us the opportunity where we might have some improvements, where we might use some data in the analyze phase again to figure out why we're not performing right. What are those opportunities to help reduce the variation in our process so we can perform what the customer wants. And once we identify those, that's where we identify then the fixes that we want to put into place to reduce those gaps, to minimize those gaps between how we're actually performing and what the customer wants, so we eliminate those defects. Once we've got the improvements, then we want to put some controls in place to help sustain those fixes and sustain those improvements. This is how we're following through the entire DMAIC methodology. Now, how do we calculate the actual process capability? Well, here's the illustration we've used before to illustrate how we would drill down to figure out the process capability, where it starts off with the first question: we need to understand what data is that we're measuring. Well, based off of the type of data we're measuring, for example, if it's continuous data, the next question we're going to ask ourselves is the process stable? We might use an IMR chart to figure that out. Well, if the process is not stable, then we really can't calculate the process capability. There's probably some special causes within our data that we need to fix and remove those special causes so that way we can get the process to some stable point where we can trust whether it's really stable or not, and then begin to assess the capability of that process. So once we know then the process is stable, then we might go to the third question, which is figuring out, is the data normal? And we'd run a normality test on that. If the data is normal, then we'll find ourselves drilling down to this fourth portion here, which is the capability analysis for normal data. But if the data is not normal based off of the normality test, we'll find ourselves using the capability analysis for non-normal data, where we'd use a Box-Cox transformation, for example, to run that particular analysis. However, if we go back to the original question and we're finding that the data we're using is actually discrete data, then we'll find ourselves using the capability analysis that's more for binomial type of data.
Okay, now let's dive into these steps by attacking the first step of answering the question, what data is being measured?
Well, in order to answer this question, we need to define the type of data that we're looking at, as well as some key data characteristics. So some of the items we reviewed before in another lesson in the measure phase on data types, we've looked at continuous data versus discrete data, where continuous data is really a variable type of data that's measured on some continuum. That is, it's virtually infinite in scale or divisibility. Some examples of that would be like numerical values we might measure in terms of dollars or time or distance or degrees. Now, discrete data is attribute data that's measured by counts or classifications. It's usually going to be much more limited in scale or divisibility. So examples of that would include yes or no values, pass, fail, or colors or locations, or something that's used eventually for measuring percentages or something like that. Now, as well, we went into the measure phase lesson and defining defects. A few things that we want to go over here, some additional characteristics, for example, like a unit. A unit is something that can be quantified by the customer. It could be a service or transaction or some product or something that's defined by them as an individual unit for how we're going to be measuring things. The opportunity is something that is a total number of chances per unit that we might have for a defect. Now, a defect is referring to a single instance or of some sort of non-conformance to the customer's requirements. That is, it could be a metric that's reflecting where we fell outside the upper or lower spec limit as defined by the customer. Now, defective is referring to a unit that contains one or more defects in it. It's measuring the severity of how defective that unit is. So here's an illustration we've used before in comparing defects with defectives. For example, if each of these different squares represented a unit, and we might have within each one of these units 9 different opportunities, or 9 circles representing each one, that could be an opportunity for potential failure or potential defect. We might say, is this unit a defect? Yes, it is, because there's at least one of these opportunities, one or more, that are a defect. And in this one, we would say it's how defective is it? Well, it's 2 out of the 9 that makes it defective. The second one here, there's 9 opportunities, and yes, the entire unit is a defect. And how defective is it? Well, it's these 3 out of 9 possible opportunities, and so on. And we might compare that then to the fourth one here, where there's nothing that's indicated here among the 9 different opportunities that there's any defect at all. So the unit is not a defect, and there's 0 as far as how severe or defective that particular unit is.
Now let's go to that next step by asking, is the process stable?
Well, to answer this question, we need to use control charts to assess the stability of the process itself. Now, we're going to review a few things from the prior lesson in the measure phase that was on testing for special cause variation. And we looked at control charts where we can plot the data points using continuous data over time and help define the following few things. And here's the example that we had used in that particular illustration. So it's where in these control charts we're plotting, first of all, the observations. That's each of these data points that are plotted through here over time. And then we have the mean, that is the average for all the data points that's reflected here by this green line. And then we have the lower control limit down here, which is defining the 3 standard deviations below that mean. Got to keep in mind that that is very different from the lower spec limit, or LSL, which is referring to what the customer's requirements are. Instead, the lower control limit refers to 3 standard deviations below the mean. Upper control limit refers to 3 standard deviations above the mean. And just like with the lower control limit, it's very different from the upper spec limit, or USL, again, which is what the customer wants, regardless of how many standard deviations it happens to be from the mean. And also special cause tests. These are among those 8 different rules that we had gone over in that lesson that help identify where there could be some special causes. Like in this example, where it happens to fall outside of the lower control limit here, or even if it were to fall outside the upper control limit up here, but in this case where it falls outside of it, it's shown as red because it identifies where there was some sort of observation or one of these data points that could be a special cause. So this is how we would look at to see if the process is stable using a control chart like this.
Okay, we'll now cover the next step by asking, is the data normal?
In order to answer this question, we would need the test for the data's normality. So we can review again the measure phase lesson where we talked through about normal and non-normal distributions, where we had used the normality test to assess the normality of the data. So in those tests, we would use the Anderson-Darling test, for example, in order to test normality, or to use like a probability plot to test for that normality. Normality test, or the probability plot, will plot the data on a logarithmic scale, and the normal data will appear like a straight line. And Minitab will try to fit a line based along those data points that it had plotted. Now, the p-value, if you're using like the Anderson-Darling test, if it's greater than 0.05, then we would consider it to be normal. Otherwise, if it happens to be less than 0.05, for example, if we're using 95% confidence, then we would say that the data is not normal. So an example that we have here, this might look like a normal distribution. If we plot that data, we would plot it like this using the normality test, or like a probability plot. And we would look again for the p-value that's used for the Anderson-Darling test. And the p-value down here would show that it's greater than 0.05, which indicates to us that it is a normal distribution after all. And non-normal distributions, though, have some sort of bias or skewness that's in the data. The non-normal distribution distributions are not random, and therefore they're going to have something that does influence their results. The bias that might occur in the data, like from a non-normal distribution, either could come from how the data was collected itself. It could be some bias in the way that the data was collected, or it actually could be a special cause that's in the data, something else that exists within the data that's causing it to be biased. It could be either one of those two things, but in those cases we might use the median as a way for measuring central tendency, since the median, or that 50th percentile, will never shift like the average or the mean could shift if we have non-normal data. So in the illustration we might have here, this looks non-normal. It does not look like a typical bell curve when you look at this histogram. And if you were plotted out again on this logarithmic scale, like from a normality test or a probability plot, it doesn't have that straight line. Minitab does it in this case try to fit a line on here, but you can see it falls outside of the line that it's trying to fit. And when you look at the p-value for the Anderson-Darling test, it falls well below 0.05. And because of that, we would say that this type of distribution is not normal.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
Well, to this point, we would try to walk through using some data through that drill down if we're trying to figure out how we're going to calculate the process capability. So what I'd like you to do is try to refer to two continuous metrics that you've identified in the first lesson when we began looking into process capability. For each one of those metrics, try to answer the first three steps of this drill down as we're trying to calculate the process capability. First of all, what data is it that's being measured? That is, what's the type of data? If it's discrete data, then we might plan to advance to step 6, which is about the capability process for binomial type of data. If it's continuous data, then we want to go on to this next question. But in either case, whichever type of data it is, be sure that you also identify what's a unit, an opportunity, a defect, and a defective. So this next question we're going to ask ourselves when it's continuous data is the process stable? If it's not stable, then you need to stop any further analysis for that particular metric, and we need to go back and collect additional data that reflects a stable process. That is, try to find out what's making it not stable, try to eliminate any special causes you might see until you can get it to a stable method. Once you've got the data that reflects a stable process, then you can move on to this next part where we would try to figure out the next question of asking, is the data normal? If it is normal, then we want to advance to step 4, which is the capability analysis for normal data. But if it's not normal, then we're going to plan to advance to step 5, where we're going to do the capability analysis for non-normal data, where we might apply a Box-Cox transformation.
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.